Yeah, it's funny, somebody on YouTube complained about the sound in the room. They were like, man, your room's sound is crap. I agree with you entirely. It really did sound like crap in that room, but we had to suffer with it more than you did. So anyway, it's fun. Okay, so now we're going to get our hands dirty. We're not going to get them that well. Yeah, they're going to be pretty dirty. Anyway, we're going to get our hands dirty today with some technical stuff, which I should say, is everybody eating them? You passed them out to everybody, right?
Oh my gosh, no.
Wow.
That's weird. You're right.
Yeah.
Anyone want some candy canes? Oh, excellent.
Okay, just let the box migrate around the room.
Yeah.
That's fine. Okay. All right. So, okay. Back. Pay attention to me. Pay attention to me. I'm trying to teach. Okay. So, all right. So what we're going to do today is we're going to start our investigation of symmetry. And symmetry is going to play a very, very central and important role in this course in many different aspects. We're going to find that symmetry is sort of a way of defining special relativity, which is the framework in which we're going to do most of our calculations. But then it also turns out that symmetry is what underlies the three forces that we're going to look at in detail throughout the semester. So symmetry really plays a really important role, so we need some sort of mathy language with which to describe symmetries. All right. Okay, so I'm gonna, before I start applying this to, give them back to him, and now let's all pay attention. Eyes forward, not at the candy canes. Although I didn't get one, damn it. So anyway, all right. So there's a couple of different types of symmetries which we might consider. There is first and foremost what we might call the static symmetries, and these are, if you will, the idea that if I have a perfectly equilateral triangle, then if I rotate it by 120 degrees, the result looks exactly the same. So that's a symmetric object under that given transformation. So this is static in the sense that, you know, you can look at it and then you can transform it. You can look at it again and say, oh, it's the same shape, or it's the same orientation, or whatever. Okay? We are, in this class, though, really going to be interested in dynamical symmetries. And what I mean by dynamical symmetries can be sort of encapsulated in a single statement, actually. It's pretty surprising. Oh, thanks. Appreciate it. It's kind of crunched up, though. I like
They're all crushed, I promise.
Oh, okay. Maybe that's why the box is left up here. Anyway, all right. The sort of single statement that we can use, which encapsulates all of our use of symmetry in this course, is if I have a Lagrangian, and a Lagrangian, you know, you might have at some point when you were taking 350, if you've taken 350, you might have saw a Lagrangian as another way to do something, but Newton's laws are just as good. Well, Newton's laws aren't as good as a Lagrangian. Lagrangians are just very broad in their applications. I take them as a much better definition of physics than Newton's laws. Or Hamiltonians for that matter, because Hamiltonians aren't really suitable for relativistic scenarios in a smooth sense like a Lagrangian. But anyway, when I just write down Lagrangian, what I mean is the physics. Okay, and we'll work with Lagrangians in detail, but I just mean a physical system which is described by some Lagrangian. Then if we undertake some transformation, and these transformations can be different, then in principle the Lagrangian can change to some new form, okay? But if the new form of the Lagrangian is identical to the original form of the Lagrangian, then we say that transformation represents a symmetry, but it's a dynamical symmetry because the Lagrangian is responsible for the dynamics of the physical system, okay? So, I mean, in a sense, triangle goes to triangle, L goes to L. They do kind of look the same, but there's a lot more in the Lagrangian than there is in a triangle, okay? All right. Now, no matter what type of symmetry we're considering, whether it's static or dynamical, the spirit is the same. We enact a transformation, and then after the transformation, whatever we transformed comes back to its original form, all right? Now, naively, it might seem that if we want to build a symmetric theory, or we want to build a symmetric object, then we're always going to be faced with what we might call an invariant. Okay? So you might say, oh, the triangle is invariant, therefore, you know, it's invariant under that thing. And then the L just doesn't change at all under some transformation, so it comes back to itself. Okay? So what I mean is that you might imagine that your Lagrangian, which is built out of many small pieces, maybe it's true that every single piece of the Lagrangian has to be invariant. Because if every single piece of the Lagrangian is invariant, then the Lagrangian is invariant, right? Okay? It turns out if you restricted yourself to that category of things, you couldn't do very much. Fortunately, that's not what we're going to do. We're going to discover that the pieces that a Lagrangian is made of do transform, but their aggregate is invariant. And we'll see exactly what I mean by that towards the end of today's lecture if we get to it. Okay? So we are going to be looking at things which do transform, but we're going to combine them in such a way that their net system is invariant. So what's really important for us to start out with is getting a mathematical language to describe transformations. Okay? Once we kind of understand how to mathematically describe transformations either of this type or this type, then we can go into the question of, okay, now how do I build an invariant out of that? Okay? So let's look at transformations. Transformations, as it turns out, come in many, many different types. And I'll just give you a list of words, and then we'll go through the words one at a time. But transformations can be global, or they can be local. They can be discrete, or they can be continuous. They can be finite, or they can be infinite. They can be compact, or non-compact. And then lastly, they can be internal, or they can be space-time. Okay. So there's lots of different words which can be applied to various sets of transformations, depending on what transformations you consider. So let's go through these words. I'll give you all the intuitive definition of what each of them mean. So let's start with global versus local. And is my writing big enough for those of you in the back of the room to see it? I'm just trying to fit everything on the board versus having to write something and then erase and write something and erase. But if at any point I'm writing too small, just let me know and I'll write bigger. Okay. So let's talk about a global versus a local. So we're going to talk about examples because examples are the best way to help you understand anything. So in example 1, what we're going to do is, as our system, we're going to consider a series of dots, 9 of them, okay, in that particular configuration. And then the transformation we're going to consider is a shift in the dots, locations, okay? So a local or a global version of this might give me something which looks like the following. That's if I take each of these dots and I translate it, or I just shift them in their location, and I do it the same to every dot. Okay? Would you say that this system is symmetric under that transformation? Does this look like this? Yes. So it's symmetric. Okay? But then we can consider a local version. And in a local version, what we do is we allow each dot to be shifted independently. So if I take each of these dots and I let them undergo their own independent shifts, I might end up with a picture that looks like this. Okay? Where this dot became this dot became this dot, this dot became this dot, et cetera, et cetera. Okay? You can get this, but they're all undergoing different shifts. Now, is this the same as this? No. Okay? So we'd say this is not symmetric. So we have a situation where we have a system, we're considering a transformation. If we do it globally, the system is symmetric. If we do it locally, it's not symmetric. Now that might leave you wondering, well, how the hell are you ever going to have a local transformation that's symmetric? Let me give you an example. So example 2. Our system is going to be a set of circles, and our transformation is a rotation of each circle about its center. Okay? So if I do this globally, what do I end up with? Well, if I rotate this 45 degrees, I rotate this 45 degrees, I rotate this 45 degrees, I rotate this 45 degrees. Is it symmetric? Yes, it is. This is symmetric. Okay. If I do it locally, if I rotate this by 45 degrees, I rotate this by 90 degrees, I rotate this by 270 degrees, and I don't rotate this at all, is it symmetric? Yes, it is. Okay? So this is just sort of this is a static example. These are not dynamic transformations. Those are a little hard to draw. So we'll focus on static ones to get all these words out, but then we'll work with dynamical ones. Okay, but here you go. These are global transformations versus local transformations, and sometimes it's symmetric, but sometimes it's not. Okay? Now, quick question. If something is invariant under the local transformation, is it automatically symmetric under the global transformation? If it's invariant under the local forms, is it also invariant under the global forms?
Is it invariant under all local?
All local forms.
Then it would have to be.
Then it would have to be, because one example of a local transformation is doing the same thing to everything. That's an example of a local. Of course, there are more local transformations. If you're invariant under all local transformations, which notice, any local transformation, this is invariant, because I'm just taking these and spinning them. If you're invariant under all local transformations, then you're automatically invariant under global. However, if you're invariant under global, you're not guaranteed anything about local. Okay, make sense? Good. All right, now let's talk about discrete versus continuous. All right, so for a discrete system, it turns out there are two categories. We can have a finite set, or we can have an infinite set of transformations. Okay? Let me give you examples of each. So for example 1, consider an equilateral triangle, and our transformation will be a rotation by 120 degrees. Okay? It's finite since the set of transformations includes doing nothing, rotating by 120, and then rotating by 240. Okay? So you only have 3 transformations that are possible. Because if you try and go beyond 240, you just get back to R360, which is the same as the identity. Okay. However, we could instead consider a set of discretely spaced dots, which goes from minus infinity to infinity. And then we can consider transformations in the positions of the dots. So I might call this the T1 transformation, where I take all the dots and I shift them to the right by 1. And then there's a T2 transformation. And I'm showing this for one pair of dots, but I do it for all the dots. I can do a transformation by T1, where I just shift everything to the next position over, or T2, where I take everything and shift it 2 positions over. How many of these transformations are there possible? An infinite number, okay? So this is infinite. Okay? So again, for discrete sets of transformations, the story can be finite or infinite. That makes sense, right? Good. Because now we're going to turn to continuous. Do you think I will have the same 2 categories for continuous transformations? These are transformations which you can do by an arbitrarily small amount. Arbitrarily small. What do you think? No, because these are always what? Infinite. Right. It's a continuum, and a continuum always has an infinite number of elements. Even if it's bound by the numbers 0 and 1, there's an infinite number of numbers between 0 and 1. Okay? So the finite or infinite's not going to work. What will work, though, is compact versus non-compact. This is where these words become important. So let me give you examples. So example 1, if I take a circle and I think about rotating the circle by an angle theta, well, theta lives, so this epsilon looking thing just means it's contained on the set. I'll write this rather often, so that's what that means. This is contained on the set, which starts at 0 and goes up to 2 pi. The square bracket means it includes 0. The round bracket means it gets all the way as close as you want to 2 pi, but it doesn't include 2 pi. Why do we not include 2 pi in the rotations? Because it's exactly the same as 0. Okay? So if I included 2 pi, I'd be including 0 twice, so I won't do that. So I get everything up to ridiculously close to 2 pi, but not 2 pi itself. Okay? This set of possible values of the parameter which is describing the transformation, this is compact. This is a compact set. There's a starting and an ending. Okay? It's compact specifically because 2 pi is identified with 0. I'll give you a contrast in just a moment. But let's just go ahead and look at example 2. For example 2, well, we could just generalize this guy. Okay? Now, we can just consider transformations along the continuous line, and we can just label these TD, where D is the distance that you're translating. This thing's obviously symmetric under any value of D. Okay? So D lives on the interval from minus infinity to infinity. So the amount that I'm translating by can be anywhere from minus infinity to infinity. This is what we call non-compact. Okay? Yeah?
Compact and non-compact is different to open and close.
It depends. It depends. So let me now go ahead and say this to you. If I was considering a set of transformations which went from -1 to 1, where I do not include these, this is technically non-compact. Compact, you have to have your boundary terms included. Now you might wonder, what about this? This is included on one end but not included on the other. Well, you have to remember there's a periodicity condition here. 2 pi is actually the same as 0. So this is actually sort of like a square bracket, except when you get to the end, you come back to the beginning. So this is kind of a weird scenario. But if I had a transformation which was defined with a transformation parameter that went from -1 to 1, where this is not the same as this, then this is also non-compact. But that's a technical thing we won't worry too much about. Okay? I will give you examples in what we're actually going to use this for of compact versus non-compact when we do the Lorentz group in special relativity. Okay, so I've ticked off global, local, discrete, continuous, finite, infinite, compact, non-compact with those examples. Dang, that was pretty good. Okay, we got 2 more words. We've got space-time versus internal. All right. And it turns out that if we coordinatize space-time, then space-time transformations are just coordinate transformations. Okay? And this will be obvious when we start using this as an example. But then you might wonder, well, what is an internal? Well, an internal transformation on a system is a transformation which does not do anything to the coordinates. Okay? So if you have a transformation of the system and it's not doing anything to space-time, what's it doing anything to? Well, you have to have what's called an internal degree of freedom in your system. And this can be various things. We'll talk about it. We'll definitely talk about it. But if you have an internal degree of freedom, this is something which can change, but it has nothing to do with space-time. It has nothing to do with motion or momentum or anything. That kind of transformation is an internal transformation. Okay? Now let me tell you the roles that these will play. When we coordinatize space-time and talk about transformations of coordinates, the symmetries associated with this are what is going to give rise to special relativity. Special relativity can be formulated as a symmetric theory under space-time transformations. When, however, we are interested in the forces in this class, electromagnetism, the weak nuclear force, the strong nuclear force, all of those stem from the presence of internal symmetries. And we'll see that played out in detail in due time. Okay? So this distinction is very important. We're going to see each aspect of it played out. But the good news is that no matter which of these cases we're talking about, the mathematics that we're going to use to work with transformations is kind of the same. So let me get this on the board. Are there any questions about these examples before I erase them? Okay, good. All right. Okay. In order to get a more mathematical way of describing transformations in general, we are going to have to rely on groups and their representations. is kind of interesting. I don't know who picked this out in math, but you might wonder, how is a group defined? Well, a group you might think of as just a set of things. Like that's a group, right? Right? It's a group of three, okay? Well, now, in mathematics, they'd actually call this a set. A group is a set where they dance. No, I'm just kidding, they don't dance. They partner up. Okay, anyway, I know, it gets dirty really quick, and I'm sorry if I offend anyone. Okay, so a group, let me give you the definition of group. A group, G, is a set of elements, and I actually in my notes I write collection, but it is also just a set. Say A, B, dot, 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 okay, with a composition operation, which I'm just going to draw by a big dot, okay, that satisfies the following. Okay, now I want to just go ahead and really say this out loud. I have a set of stuff, and I can take two of them and I can compose them with this dot. This dot doesn't mean anything, in the sense that it doesn't mean multiplication. You can compose the elements of a group in many different ways. Each way that you compose them is part of the definition of a group. Okay? So I just want you to get away from the idea that this dot means you multiply, because it can be way more complicated than multiplication. But this is just the generic term for taking two things and combining them. Okay? So the first property is what we call closure. And closure means if A and B are elements of the group, if A and B are on the set of elements of the group G. So this G is this full set, and if A and B is on that set, then, the arrow just means then, A composed with B, again, this is the composition for the particular group, it can be of many different forms, then this composure of A and B must also be an element of the group. Whoa. That's what closure means, okay? Means if I take two of these and combine them, I better get another element of the set. It's pretty simple. Two, the identity. There is some, and we call this different things. In this class, I'm just going to call it I. In other classes, I might call it E because I is too restrictive, but I'll just call it I. There is some I on G, so there is some element of the set of elements of the group that we can call I, such that, that's what I'll just write for such that, if I take I and compose it with any element A, I get back the element A. For any A on G. Okay? That's just a rigorous definition of what you know to be the identity. If you take the identity and you apply it to something, you get the same damn thing back. It's that boring. I'm just being careful because I'm saying that I must be an element of the group, and that I dot A equals A for any A on G. Okay? 3, inverse. For any A on G, there is an inverse element, A inverse, which also exists on G, such that A inverse composed with A gives me the identity. Okay? And then the fourth, and this is the one that kind of you're like, what in God's, but it just turns out to be important. but it's natural for most of the transformations we ever consider, so it's really one I can't demonstrate it being inappropriate. But if I want to compose B with C and then take whatever this gives me, remember this is going to give me an element of G, and then I can take that element of G and compose it with A. That's how I interpret this. This is maybe D, and it's again an element of G, and then I take A and compose it with D. This must be the same if I take A compose B and then use that composed with C, where this might end up being an element F. Okay? So that's associativity. That's an old math property you probably remember and never really think too hard about. Okay? So here's the important thing. If I give you a set and a composition, that is a way of combining two elements of the set that give you another element, if it satisfies all four of these conditions, then that set forms a group. Or sorry, that set and the composition form a group. Okay, so a group is a set and a composition. Just a single composition. Okay. Now, it could be on the homeworks, I don't know, but I'll just give you an example. If I take the integers, and I consider, and this is all of the integers from minus infinity to infinity, and I consider addition, does that form a group? Well, let's first ask, is it closed? If I take an integer and another integer and I add them together, do I get an integer? Yes, I do. Let's look for the identity. What is the identity? What can I add to any integer and get back the same integer? 0. Let's talk about an inverse. If I have 1 and I want its inverse, so that if I add them together I get 0, what is it? It's -1. Oh, and then associativity. Addition is associative. So this forms a group. Okay? Let's do it again. Z with multiplication. Closure. If I take two integers and I multiply them, do I get an integer? Yes! If I multiplying, what would the identity be? 1. Yes! Inverse. No. Everybody realize that? What's the inverse of multiplying by, or what's the inverse of 2? It's 1/2, which is not an integer. Okay, so not a group. All right? So you have to be really careful and consider the composition and whether it satisfies all four of these properties as to whether or not it forms a group. Okay? Now, two really quick notes. Notice that I did not require that A dot B equals B dot A. I did not require that. Okay? If this is true, then G is what is called an Abelian group. That is, if I take any two elements and I compose them, I'll always get the same element if I reverse the order of the two elements before I compose them. Okay? Now, if you're thinking about these examples, that's really hard to figure, because if you're adding two integers, it doesn't matter their order. So if you just want a quick example of this, think of matrix multiplication. In general, matrix multiplication depends on the order of the matrices. A dot B is not always the same as B dot A. Okay? And of course, if this is not true, then G is what we call non-abelian. Okay? Ready? Pretty much every group we're going to work with is non-abelian. There's one abelian group. Okay? So constraining yourself to this situation where groups are abelian is not going to do for us. We're going to work with non-abelian groups. There is one more quick thing, and that is if I take a subset of the set of elements that comprise G, if I take a subset of them, again, with the same composition, if a subset of G with the same composition satisfies the group properties, then it is also a group, because it's a set of things with a composition that satisfies these properties, but it's called a subgroup. Okay? Now very quickly, if I have a group, it's a set of elements, and then I want to consider a subgroup, what single element must always be in the subgroup? The identity. Because there's no way you can satisfy these without an identity. But also, if you pick any other element, its inverse had better be in the subgroup as well, because you won't satisfy these unless you have an element and its inverse. Okay? Now, you remember when I took that triangle and I rotated it by 120? And I said there's only 3 elements? That's a subgroup of rotations by an arbitrary angle theta, which I can do on circles. I can also transform the triangle, by an arbitrary rotation. It just won't come back to itself. Okay? But I just want you to realize that the triangle which had I, R120, and R240, that is obviously a subset of rotations by any angle between 0 and 2 pi. It's a subset because there's the identity, and what's the inverse of R120? R240. And what's the inverse of R240? R120. There you go. Okay, so that forms a group, a subgroup of the rotation group. Okay? All right, how we doing? Good? Awesome. Sweet as. Okay. So, all right, so I'm going to get rid of our definitions of groups. For those of you who are interested in this, I think that, does the math department offer a course in abstract algebra? Do they call it abstract algebra? Yeah. So there's a math course which really, develops these ideas in detail, and it's called abstract algebra. The name group is not in there, but groups are what they're going to talk about. And anyway, so we can abstractly define a group. For example, I can abstractly define a group where I say rotations in 2D with composition, the addition of angles. Now, what do I mean by that? Well, the set that I'm dealing with is the identity and then a rotation by a really small angle, and then a rotation by, so basically it's a continuous set. So I can't list them all, unfortunately, that doesn't work, okay? But, I just as a discrete set, I can say, pi over 2, pi, r, 3 pi over 2, and back to the identity within that set. But anyway, okay? And then might think a rotation is a transformation, but no, these are the elements of the group. And then the composition, the way I combine two of them, is I basically take the angles associated with each of them and I add them. So I is just a rotation by 0, so I can put a 0 there for the angle. But if I want to know what is r pi over 2 composed with r pi, it is r pi over 2 plus pi. It's intuitive, right? But this is how I'm defining the composition in this case. So that is an abstract way of defining a group. However, when we want to work with groups, we need something more concrete, okay? And this is where representations are going to become important. So a single group can have many different representations, some of them more useful than others. So let me give you an example of the representations of a group. And I'll use a slightly different group. So my G is going to be the set of rotations in a plane by 90 degrees with angle addition. Composition. Okay, so it's pretty much what I just wrote, but at any rate, first and foremost, I'm going to draw a representation of this, which is the most useful representation. So I'll call this representation R1. And what I'm going to do is I'm going to draw a square object. That's a square. Looks a little rectangular-ish, but I can't get sides exactly the same. And I'm going to label the corners of it, A, B, C, D. Okay? And now what I want you to notice is that if I take this object and I rotate it by the elements of this group, I will get a different result for each element of the group. So in this case, I'm going to have, first of all, not doing anything. That's the identity element. Then I can talk about a rotation by 90 degrees. That's going to, of course, take A to B, B to C, C to D, and D to A. That will look different. So I can say, oh, I took it and I rotated it by 90 degrees. Or I can take it and I can rotate it by 180 degrees. That will take A to C, B to D, C to A, and D to B. Okay? And that will obviously look different than what I started with. And then last but not least, I can do a rotation by 270. Okay? So R270 will of course take A to D, et cetera, and that will look different than what I started with. All right? So this is one representation of the group. Make sense? All right, let's consider another. Well, I can always do the identity. That's a given. If I do a 90-degree rotation, do I get something new and different? A 90-degree rotation. A will go to B, B will go, so yeah, that'll look different. So R90 is still new and different. But what if I do 180? A goes to A, B goes to B. It's kind of boring. Okay? And then what about 270? It gives me the same thing I got when I did R90. So what we're discovering is that this representation is what we call degenerate. Okay? Basically, I goes to I, R90 goes to R90, but R180 gets mapped into the identity in this case, and R270 gets mapped into R90. okay? Now don't get me wrong, that's degenerate, but then there's total degeneracy. How many of the elements of the group are unique? One, and that's got to be the identity. Okay? This representation is what we call faithful, degenerate, and fully degenerate. Okay. The word faithful just meaning if we want to completely encapture all the different elements of the group, we need a faithful representation. All right? If you're working with degenerate representations, you're not going to get the full flavor of the group because our elements might get mapped into duplicate elements. All right? We're going to see a very interesting example of, oh, we thought we had a faithful representation, but we don't. But I'll let that play out in due time. Okay, so now, so far I have, I've been very pictorial. I love pictorial physics, drawing squares, rotating them, it's so fun. But you can't write equations with this shit. What do you need? You need matrices. You need to put all this in a matrix language, because a matrix language is the language which we can actually write equations with and we can manipulate and do stuff with. There's a lot of rules that come with matrix manipulation that we can make use of. You do not have to do that. You can work abstractly. But it turns out that almost every element of these stories can be put into matrix language. So if you want to write it down in a simple form, you might as well go to the matrix language. And that's what we're going to do now. Okay? So are there any questions about this before we move on to matrices? Okay. So let's matrix it up. So I'm going to work with the same group. But what I'm going to do is I'm going to give matrix analogs for the various configurations. So remember, we want a faithful representation of this, so really and truthfully I should draw all four representations, or all four configurations. Good, I just want to make sure someone was paying attention. Oh boy. Thank you. All right, so those are our four configurations, and what I want to do is I want to assign a matrix to each of them. Many different ways to do this. I'm going to give you what to me is the most obvious choice. I can call this 1, 0, 0, 0. And then I can call this 0, 1, 0, 0. And then I can call this 0, 0, 1, 0. And then I can call this 0, 0, 0, 1. Okay? So now instead of looking at these pictures of the squares, I just replace them by these matrices. And now what's nice is that the transformations, which are the actual elements of the group, can be written as matrices, square matrices. So for example, the identity, if I hit any of these with the identity, what should I get back? The same thing. That's the same picture or the same matrix. I'm calling this a matrix. You might think it's a vector, but a vector is a matrix as well. So this is a matrix. It's just a column matrix. But anyway. So I want a square matrix, which if it hits this, or this, or this, or this, it gives me back the same thing. What is it?
The identity matrix.
Say it again?
The identity matrix?
Yeah, well, what is the identity matrix? Yeah, it's ones down the diagonal. There you go. So that is one of the 4 elements of our group. Next, we have R90. What does R90 look like? Don't worry, it's much harder. I'll just write it down for you. I mean, you could figure it out. Okay? Now, I want you to realize if I take this R90 and I hit this with it, what will I get back? I'll get back this. What if I hit this with R90? I'll get this. What if I hit this? I'll get this. What if I hit this? I'll go back to here. So the R90 can be applied to any of these, and it will just transform you one to the right. Okay? Now, R180. Can anybody guess what that one is? So there's different ways of thinking about it. R180 should take this to this, this to this, this to this, and this to this. But if I want to write down the matrix which does that, what's the quickest and dirtiest way to get that matrix? Sam?
Put the bottom row of the R90 on top.
Well, so that's using your inspection of how this is acting on these, but there's actually a cheat to figuring out what R180 is.
The matrix is defined by what it sends the basis vector. So each column is just the basis vector it sends.
Okay, so you guys are using the intuitive way to do it. You're kind of like using your intuition. Oh, these are, I'm just shifting these around. But if I want to know what R180 is, and you didn't actually have this picture, what would you do?
Repeat R90 times R1.
Yeah, you just take this and square it. Okay? Yeah, I mean, that's another way to do it. The way you guys are talking about is perfectly fine and legitimate. Okay? So R180 ends up being 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0. And then last but not least, R280, which of course you can get, or sorry, R270, which you can get by combining R90 and R180, is going to be 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0, 0. Okay? Now, is this Abelian? In the sense, if I take R90 and compose it with R180, is that the same as R180 composed with R90? What do you think? So if you think about it in terms of matrix multiplication, you might be nervous. You might be like, oh, I don't know, is the product here the same as the product here? But go back to the abstract definition of this group. You basically take the two angles and you add them. Well, if I add 90 and 180, do I get the same thing as when I add 180 plus 90? Yes, I do. So it is Abelian. And the matrix multiplication will also evidence that. Okay? Now, one quick note before I move on. I used real matrices. All the elements of these are real. You could use complex matrices. Okay? You could do it with complex matrices. You'll get to explore that in homework. All right. Now, any questions about this before we move on? Yeah.
It is possible because there is a property, I don't remember what it is, homomorphism or something, right?
So I'm going to talk about homomorphisms in just a minute. Okay? But let me, get rid of this. Okay. So for finite, or for discrete groups that are finite, so for finite discrete groups, which we're going to work with regularly, we can form for finite, and if it's finite, it's automatically discrete, right? Okay, so for finite groups, I'll just put in discrete just so you know it has to be a discrete group. Discrete groups, the group structure can be shown via a multiplication table. Turns out a multiplication table is yet another way to define a group, a finite discrete group. Okay, you here for particle physics?
Oh, no.
What class are you here for?
K-12 experience? Or
And
field experience?
that's supposed to be in this room at 6?
Yeah.
Yeah, so is the room next door empty?
It doesn't look like it.
There's still people in there?
Yeah.
That's where I'm supposed to be teaching. And I teach until 6:15.
Okay.
How many people are out in the hall waiting for this thing that you're going to?
Looks like 5, maybe more right now.
Oh, wow.
Because of the noise, just having people, so.
We should just talk to them. Is that even a class? Because we're definitely scheduled in there.
We should
That
get
no one would be hiring at 9 p.m.
It's like, get the hell out of the way! Okay, anyway. Yeah, okay, so, sorry. All right, so for the, for the group that we worked with earlier, okay, to form the multiplication table, we basically want to take it and form a table. And then we want to list the elements of the group across the top and down the side. Okay? And then I basically just fill in what I get when I take the identity and I compose it with the identity. What is that? The identity. What about the identity composed with R90? R90. Notice, when I take something from here and combine it with something from here, that's I compose R90. All right, what if I take this I and go combine it with this R90? What's the order there? This is R90 composed with I. That's just an important distinction. But it gives you the same thing, R90. Because I composed with anything is always going to give you back that same thing. R90 composed with R90 is obviously 180. And then I can very quickly fill this in. The identity composed with everything gives you the same thing back. And then this is the identity. And then 90 and 270 is the identity. That's the identity. R90, R180 gives me R270. R270. R270 and R270 give me R180. R270 and R180. Yeah, it's R90. You're just adding the angles and you're, if you go past 0, you just roll it back. Okay? Couple of notes. If G is abelian, then the multiplication table is symmetric across the diagonal. Okay. This is an abelian group, so it's symmetric if I flip everything across the diagonal. If If it's a non-abelian group, then it's not symmetric. That's why you have to be careful about this meaning I composed with R90 versus this meaning R90 composed with, well, actually the identity is not a good one. So this means R90 composed with R180. This means R180 composed with R90. I'm reversing the order in which I say those. So if this was a non-abelian group, these two entries would be different. But this is abelian, so it's symmetric. Okay, everybody follow that? You don't want to be here. You want to be in R130, you're 130, the computer left you.
Thank you.
Sorry, you're welcome. Should have just let her sit down and kept going. That would have been so mean. Notice R180 is I and R180 is a subgroup, okay? R90 is not a subgroup. Okay, neither is I270. Okay? If we thought about this square here in 3 dimensions instead of 2, we would have more transformations, right? Because we could basically take it and flip it over. And you could describe that using the matrix language as well. Okay? Now, okay, any questions about this before I? Yeah.
I think I missed it. How did you, from the table, say that I and R180 are a subgroup?
So I and R180 are a subgroup because it has the identity. And the inverse of R180 is R180. So the inverse is there. Here, what's the inverse of R90?
R270.
It's R270, but it's not an element of this set, so this is not a group. Yeah. Okay. All right. Okay, so well, while I'm on this is not actually in my notes, but I'm going to go ahead and say this to you because this is actually useful. For discrete groups, okay, they can become infinite, and continuous groups are obviously infinite. It does help at times to realize that there can be a set of elements from which you can generate the entire set. Okay? So if I consider this set I, R90, R180, and R270, what subset of this could I use to generate the entire set? Can I use the identity? So if I take the identity and compose it with the identity, what do I get? And if I compose that with the identity, what do I get? And if I compose that with the identity, this gets really boring really fast. No, you can't make anything else with the identity. What about R180? If I take R180 by itself and compose it with R180, what do I get? The identity, yay! What if I compose that with R180? And get back to R180. So I'll never get either of these from R180. What about R90? If I take R90 with itself, R90 with this new element, R90 with this element. So the R90 is what we call a generator of the set. It's not a subgroup, but this element by itself will create all of the other elements. Any other generator? R270. Okay. The notion of generators is going to play an incredibly important role when we start looking at continuous groups. But I just want to go ahead and get that out there. Okay, so I'm going to, well, we'll see. I'll decide what I'm going to do in a minute. Okay, so now I want to talk for a moment about the equivalence of groups. It turns out that groups can be defined in different ways, but they can actually, in a mathematical sense, be exactly the same. And it turns out that if you're dealing with a finite discrete group, the simplest way to take two of them and ask, are they the same, is to ask, are their multiplication tables the same? And if they are, then those two groups are what we call isomorphic. Let me give you some examples. So if I do, I don't know what the hell I wrote. Oh yeah, anyway. So if I take the rotation by the identity and the rotation by pi, yeah, so this is yeah, I guess that's what I meant to call it, is two rotations. Okay, where the composition is the addition of the angles. Okay, then obviously, that's the multiplication table, okay? However, I can instead take even and odd numbers abstractly with addition as the composition. If I take even, odd, even and even addition gives me an even number. Even and odd addition gives me an odd. Even and odd gives me odd. And odd gives me an even number. Okay. And last but not least, if I take 1 and minus 1 with multiplication, are these three groups isomorphic? Absolutely. All of their multiplication tables are really showing you the same thing. I'm using different symbols, but who cares about the symbols? It's the structure here that's important. So there's a sense in which these are all isomorphic. In fact, I can give it a more generic name. I would call this Z2 with elements I and G with G squared equals I. That's the more abstract definition of what all of these groups are representations of. Okay? That makes sense? Okay, so I'm actually going to try and hit one more thing. This is going to be a little bit time consuming, but I think I can get it out. And it'll provide us with a nice step into the next part of the story. Plus, I did have to waste a bit of time arguing with them, so I think I deserve it. But anyway, are there any questions about this before I erase it? Yeah?
Could you repeat that part of generator, please?
Sorry, say it again?
Generator?
Yeah.
Could you repeat, please? Because I didn't understand.
Can I explain it?
Okay.
Explain the generator story? So I have 4 elements of my group. A generator is an element that I can use to build all of the other elements. So I can take R90, compose it with R90, and I'll get R180. So the left-hand side is built only out of R90, and the result is R180. I can take R90, compose it with R90, and then take the result of that and compose it with R90, and that will give me R270. And then I can take this and do it again with R90 and get the identity. So R90 is this sort of fundamental building block from which I can build all the other elements. You cannot do that with the identity. If I take the identity and compose it with the identity, I get the identity. I don't get anything different. If I try it with R180, I can't do it, because I'll never get these. But it turns out with R90, I can get all the other elements, and also with R270, I can get all the other elements. So these are the 2 generators of the group. They're going to play a very important role when we're trying to look at continuous groups, which we'll do in detail. Any other questions? Okay, so let me very quickly go through what I have left. Because I have been talking all about transformations. I have not talked at all about invariance. So the question you might have burning in your soul, your souls are on fire, is, well, Barnard, you've got all these things that change. How do you make it invariant? Okay? Well, if you think about it, can have an object which doesn't transform at all. That's invariant. It's boring. Okay? But I can also have an object which does transform, and I combine it with another object whose transformation basically cancels the transformation of the other one. Does that make sense? How many of you have seen something like that? What's it called? No, it's not an answer. It's not a good one. That's okay. It's a good guess. It's an awesome guess. It's called the dot product. The dot product, if you rotate the coordinate system, this vector will change. And this vector will change. But the dot product of the two vectors will be invariant. It's a scalar. That make sense? So the dot product is a way of taking two things which transform under, in this case, coordinate transformations or rotations. And if they transform in exactly the opposite way, as it will, then this is invariant under the transformation. Now the dot product is kind of like this, I don't know how it was introduced to you in your calculus class, but poorly I'm sure. But I would like to give you a more generic definition of this and something that you can actually use well beyond the context of dot product. So here's what we're going to do. We're going to say if A is an element of the group G, then an element of the representation under the action of A goes to AR. Okay? So for example, we might use the matrix representation where R is a column matrix and then the transformation A is a square matrix which acts on the column matrix and gives you back another column matrix. Remember that? Okay. Then we can define the dual R twiddle by having the transformation that R twiddle goes to A inverse transpose R twiddle. Okay? So if R under the element A on G transforms as AR, then the dual to R, which I'm going to call R twiddle, should transform as R twiddle goes to A inverse transpose R twiddle. Okay? Now that might look like a real headache, but that's actually what works. Because if we form R twiddle transpose R, okay, then the transformation is, well, R twiddle transforms into A inverse transpose R twiddle, and all of that is transposed. So I'm just saying R twiddle is given by this under the transformation. So I'm replacing R twiddle with this, and then I have to transpose it. And then R transforms as AR. Looks like a nightmare, right? It actually works out. If I have the product of two things, and I'm transposing, how do I relate that to the transpose of each of them? So if I have A, B transpose, how is that related to A transpose and B transpose? Say it again?
B transpose A transpose?
Yeah, you have to reverse the order. Everybody familiar with that rule? It's from matrix multiplication, but it's in general. Okay? So if I want to transpose each of these, I should reverse their order. So this is going to be R twiddle transpose, A inverse transpose transpose, AR. Transpose transpose is the identity. So this is R twiddle transpose, A inverse AR, which is R twiddle transpose R, which is what we started with. Okay. So if we have a representation, then we can form the dual representation, which transforms in this particular way. And now we can take an element of the dual, combine it with an element of the representation, and that combination is invariant. Now we're getting somewhere, because we can imagine building our Lagrangian out of things which change, but we pair them up. And we might do more than pairing, but at any rate, we at least pair them up so that the change in one cancels the change in the other. Okay? Now, don't get me wrong, the dot product is basically this, where this is the dual and this is the vector. The dual and the dot product language is just you transpose and that's it. But we're going to look at more complicated scenarios. That's why I didn't want to use the dot product as an example, because the dot product is just really, really super simple. Okay, all right, so I'll finish there. I do have an example of using the matrix form of my squares being rotated by 90 degrees. So I do construct representation and then the dual representation, and I show that all this works out. I'm just going to leave that in the notes and you can look at it. It would be a lot to write on the board. But yeah, we'll just end there and we'll continue next time. All right, so later on tonight I will have the first of your homework assignment up. It'll be 2 to 3 problems, and then you'll get the rest of it after my lecture on Tuesday when I know how far I've gotten. My office hours, I'm going to put these up, but they're most likely going to be an hour on Tuesday evening, 3 hours Wednesday afternoon, and then an hour Wednesday night. I'll put the exact times up. And then you can also, I teach studio for Physics 100 from 2 to 4 p.m., and you're welcome to come over to the studio from 3 to 4 p.m. and ask me questions if you have any. Don't come in the first hour because I might be doing a presentation, but you can come over there and ask me a question if you need that as well. And my office hours for now, except for the studio, my office hours for now will be on Zoom, because we're supposed to do all our office hours on Zoom until we get the thumbs up. Okay. If you have any questions, you can come up here and ask me, but let's get everybody out.
Assume we're going to do more vectors at some point. Is our metric going to be 1 minus 1 minus 1 minus